I want to talk a little bit about one-dimensional relative velocity. And I know you can't see it right now, but I'm drawing a picture. And I'm very self-conscious of my pictures. And people start snickering when I'm in the middle of drawing them, makes me a little bit freaked out. So I'm going to draw it without you seeing it. That way there can be this grand reveal. I am drawing a person standing on the side of the road and a truck passing by them. And let me tell you, it's a magnificent picture. All right, so here's my magnificent picture. Right? Magnificent. Yeah, it's okay. It does look like a truck though, right? Pickup truck? You better participate. That's right, you'll be taking that quiz. I'm okay with it.
That truck actually looks pretty good.
Thank you. That's what I wanted to do. Was that so hard? It was not that hard to do that. See, that's all it takes. It's a little bit of, lying to Mr. Shelton to make, to placate his fragile ego. So, Tanner, can you shut the lights off for us, please, so we can get started? So here we go. I want to talk just about one-dimensional motion, mostly because I have this, this kind of silly Mythbusters video that shows like a relative velocity question, and I kind of like it. So the idea of relative velocity that we were talking about in 2 dimensions is more complicated than just this idea of relative velocity in one. And the reason I bring that up is because relative velocity in 1 dimension can really exaggerate and exemplify something known as a reference frame. The concept of a reference frame in physics is actually a very fundamental one, and one that Newton grappled with quite a bit in trying to formulate a idea about the way physics works. A reference frame is your means of perception. So when you are perceiving something that's happening, you are perceiving it from your own reference frame. But there are lots of reference frames in nature. So when we talk about reference frames, there are different types of reference frames. Oops, wrong way. There. And what I mean by that is we tend to do physics problems in what's known as inertial reference frames. Now, it's not incredibly important that you understand this concept completely, but an inertial reference frame, and this is the stupidest definition ever, but it's the only definition I have. An inertial reference frame is one in which the rules of physics work. And like I said, not a particularly great definition, and I understand that. As a student, I'd be like, don't the rules of physics always work? Well, there's the rules of physics, and then there's the observable rules of physics. What I mean by that is, it's easy to trick you into thinking something's happening that's not. That's every thrill ride you've ever been on, is an attempt to trick you into thinking something that's happening that really isn't. And so for most of the thrill rides you've ever been on, they're all in non-inertial reference frames. Because they want the rules of nature and what your expectations are to be met differently. A simple example of this is, have you ever slammed the brakes on or had somebody else slam the brakes and stuff in your car moved around? Now, you do understand that it wasn't as if something magically grabbed all the things in your car and pushed them forwards. But if you were traveling along in the car and couldn't feel the brakes, you were just observing what was happening, you would suddenly notice everything in the car, for no apparent reason, be thrown towards the front of the car. That doesn't jive with our rules of physics. We believe that movement, or the motion of an object, has a reason, an initiant, something that caused it. Non-inertial reference frames are reference frames where the rules of physics don't appear to work correctly. And that generally is because in non-inertial reference frames, the frame is accelerating. Inertial reference frames have no acceleration. So we believe the guy on the side of the road is in an inertial reference frame because his reference frame isn't accelerating. The car can accelerate in his frame, but he's not traveling along with the car. His point on the side of the road and the grass and the area that he's standing is not accelerating. So he can observe things that happen around him, and the rules of physics will apply as he intends them to. If he was in a car that was accelerating, or if his reference frame was accelerating, his observation of events would be skewed. Who's ever ridden Mission Space at Epcot Center at Walt Disney World? Okay, so some people can't ride it, and they have two versions of it now because as a ride goes, it has been fatal for a actual large number of people. And part of the reason is because it tries to fool your perception. It spins. And it spins in such a way where you are not able to observe the fact that you are spinning because you're in an enclosed car. But as the ride spins, you get flung up against the walls. It makes you feel like you're in a rocket because they're showing you pictures of rockets blasting off and stuff like that. So they're fooling your perception by putting you in a non-inertial reference frame that is accelerating and doing so to make you think one thing's happening when something else is. So non-inertial reference frames play with your ability to understand what's happening because the frame itself isn't behaving the way you would expect. We're going to focus for the time being on inertial reference frames and kind of stay within that realm, not because you guys can't handle the idea of non-inertial reference frames, but because for relative velocity, we're going to assume that at least one of our observers is in a stationary reference frame. And we'll call that the origin. The person in the origin is in the non-inertial reference frame, observing the events around them. Now, it was at this moment that somebody in first period actually asked an important question. And they asked, important's the wrong word. They asked a question that took us on a tangent, but it was an appropriate tangent. And because I want to be as consistent as possible, I do want to talk a little bit about this. Our view of physics is called Newtonian mechanics. We are purposefully looking at a certain subset of rules. And these rules are the ones that Newton has given us. Unfortunately, these rules only work for certain observable events. Now, they're really good because they work for events that most all of us are surrounded with all the time. But the rules that we're talking about here, especially the ones dealing with reference frames, only work in certain circumstances. There are 3 circumstances where the rules of physics that we have no longer apply. And you should at least know what these 3 areas are. This isn't testable. This is just one of those things where to be a smarter, better person, you should know these things. And the first is, our rules of physics break down at the very fast. So when things are going very fast, the observable rules of the universe no longer apply. Now, to understand what very fast means, it has to be about 1% of the speed of light, or faster. The speed of light, by the way, is 3 times 10 to the 8th meters per second. So we're talking really, really fast. You'd have to be traveling 1% of that to begin to notice that the rules no longer work the way you expect them to. The next place where the rules don't work are around areas that have very big objects. Very big objects curve and tear the fabric of space, and because of that, the rules that we have, the observable rules, don't work the way we want. So we're talking about large planets. Planets are hard, though. They're pretty small, but usually, something more like or 5 times the size of our sun. That'd be a more appropriate thing. So there are really big planets that are even close to that. Our sun is 2 times 10 to the 30th kilograms is our sun. And just to give you a perception, the Earth is 6 times 10 to the 24th kilograms. So, once you start getting really big, like, 10 to the 31 kilograms, that's when you really start getting into the area where things don't work the way you would expect. And the last place things don't work the way you expect is the very small. So when we talk about the very small, how small does that have to be? Well, smaller than an angstrom. So I would say in the area of picometers, which is 1 times 10 to the negative 12th meters. So we're talking about places that are the size of the differences in the orbital shells of the atom. So let's see if this triggers anybody. 1s2, 2s2, 2p6, 3s1. How many of you remember those? Okay, who remembers those fondly? You have fond memories of those. Wow. First period, that must be my problem with first period, is almost every hand went up. And in this class, no hands went up because this is chemistry. And kids who like chemistry, they're odd ducks. Don't get me wrong, chemistry's great. It's got its place. I'm pretty happy with the products of chemistry, but my experiences with chemistry were terrible in high school, so therefore I hate chemistry. Maybe you'll feel the same way about physics in a couple of years, but right now, if you remember that, those are the electron structures, or the electron levels. The electron levels don't behave the way we'd expect things to work. They are completely weird, and the math required to deal with them is way bizarre. Chemistry doesn't deal with the math that predicts those, but the math behind that is pretty intense. So the very fast requires a special kind of physics known as special relativity. It's not particularly complicated, it's just a little bit of algebra. And you can correct everything that happens when you go really fast. The very big requires something a little bit more robust, known as general relativity, which is, in many cases, harder math because you have to change the nature of space. It has to be curved and not square. Unfortunately, the very small requires a kind of math that is might as well be voodoo because it doesn't meet any expectations of math, and that's quantum mechanics. And it is not like the movies. So anything that you saw in Ant-Man is garbage, and in Endgame when they come back there and travel through time, nope. That's fun, that's good movie stuff, but it works a little different than that. But it's still kind of interesting. So none of that's in this class, which is too bad. We might do some relativity stuff later in the year just for fun, because talking about traveling really fast and the speed of light can be kind of neat. The neatest thing about talking about special relativity is the potential for traveling through time for real, not like movie science fiction, but for real. And it has some neat applications because it actually happens all the time, and you can do it in the lab. So I want to talk a little bit about reference frame just for a moment, because this part's pretty straightforward. If I have a truck traveling towards you at 5 meters per second, and you're staying still, it's pretty easy to suggest that you would observe the truck traveling at 5 meters per second. However, if you were walking towards the truck at 2 meters per second, how fast is the truck going now? Go ahead. The truth is, I can't answer the question. This question is purposely vague. When I say the truck's moving 5 meters per second and you're moving 2 meters per second, and I ask how fast is the truck going, you really should be asking with respect to what? How fast is it going with respect to the ground? How fast is it going with respect to the person? The thing about relative velocity is the fact that in two reference frames like these, the truck and the person represent moving objects. Who's moving with respect to what? Even if this person is staying still and the truck passes them, how fast was the person moving relative to the truck? Well, the person was also moving 5 meters per second relative to the truck. In an inertial reference frame, determining what's actually moving is you deciding what the origin is, and you can place your origin on any inertial reference frame. So it doesn't matter which of these things is the origin. The truck could be the origin. And from the vantage point of the truck, the person's moving at 5 meters per second. This can become more complicated when we start putting a person in the back of the truck. Let's say they throw a baseball forwards at 2 meters per second, while this guy is moving this way at 2 meters per second. Well, how fast is the baseball going? Well, the answer is relative to what? There's the baseball's movement relative to the driver of the truck. That's 2 meters per second. There's the baseball's movement relative to the ground. That's 7 meters per second. But then there's the baseball's movement relative to the person that's walking, and that's 9 meters per second. Each one of these people observes the velocity of the ball differently. Now, this might seem like a ridiculous example, but the point of this example is to recognize that reference frames are the way in which we determine who's right. If we want to know what's actually happening in a scenario, we need to be aware of the reference frame. I mean, if the guy turns around and decides to throw the ball backwards, say this way, at 2 meters per second, well, how fast is it going now relative to the person walking? The ball is moving forwards at 5 meters per second, thrown backwards at 2 meters per second, but the person is also walking at 2 meters per second. Right now, the relative velocity of the ball compared to the person is 5 meters per second. The easy way to understand it is to just decide that one of these directions is going to be positive. Choose a fixed point that's 0 and add your vectors together. So I have positive 5 here, and I have a negative 2 there, and start adding your vectors together. Now, we're going to see this in grand scale in a video than first period is, but I'm not sure how much further along you are. I want to give you 2 vectors. This is kind of what we were doing yesterday, and we got part way to the end of a question. In fact, I think in this, let's say a plane has the plane's airspeed, this is the speed relative to the air, is 150 meters per second at 30 degrees south of east, while the wind is 50 meters per second, 40 degrees north of east. And I would like the ground speed. You should ask yourself, should my calculator be in degrees or radians? Because for us, notice if there's a degree symbol, your calculator should be in degrees. I'm going to draw a little coordinate axis system for each of the vectors I have to work with. And I'm going to kind of draw out each of the things that's happening, and I'm going to do it separately. So this is the plane, 150, 30 degrees south of east. Then I have the wind, and the wind is 50 meters per second, 40 degrees north of east. So I've drawn my 2 vectors. The next part, students tend to have some difficulty dealing with, and so I want to be really clear. You have to create components from your vector. So I describe this as wrapping a triangle around the angle. You must create a right triangle, and that right triangle must be aligned with your coordinate system. So I draw the first one along one of the axes, and then draw a component that is perpendicular to it to complete the triangle. This immediately alerts me to which one of these is the opposite side and which one of these is the adjacent side, so that I can figure out my components. The opposite side is going to be 150 sine 30, which is 75. And the adjacent side is going to be 150 cosine 30, which is going to require me to reach for my calculator and figure out the answer. Calculator, I get the 130. Now I'm going to do the same thing on the other vector. I'm going to wrap a triangle around the angle. I'm lining it up in this case with the x direction because that's the one where the angle was. And then I have my 50 sine 50 degrees. I'm sorry, it's 50 times sine of 40 degrees. And that's going to be 32. And my 50 times the cosine of 40 degrees, which is 38. So I've gotten all my components now. So I can go up here in my chart and step 1, convert every vector to rectangular. I have done that. I've got 130 in the x direction and 75 in the y direction. The 130 is positive, the 75 is negative. And then I have, for the wind, 38 in the x direction and 32 in the y direction. And again, these both happen to be positive. So I have successfully done step 1. I have converted both of my vectors into rectangular. Now I just add them together. I add like components. So negative 75 plus 32 is going to be negative 43. 130 plus 38 is 168. That is my result. 168x minus 43y. So to get to the end, this is a set of instructions. Go out 168 in the x and down 43 in the y. I'm going to go back one step here. I got the 168 because I added together everything that was in the x column. And so that 168 represents 168 meters per second in the x direction.
Okay, I got. Okay.
Does that make sense?
Yeah.
I had no idea that there was like a ton of stuff in the chat. Sorry, guys. And it's all at least 10 minutes old. Is there another question I didn't answer? Because I'm seeing all these things in the chat. Didn't even bother to look. Sorry. So, Aramis, you're good?
Yeah, I'm good. I understand. Thank you.
You're welcome. For
the plane.
So the airspeed was 150 meters per second, 30 degrees south of east. So I drew the 150 in first, and my 30 degrees says south of east, so I face the east and turn towards the south. So now I labeled my sides opposite and adjacent based on the 30 degrees being the angle. So once I did that, opposite goes with sine. I mean, I didn't write it all out, but sine theta is opposite over hypotenuse, and cosine theta is adjacent over hypotenuse. And I happen to have in this one that theta is 30 degrees.
Wait, but I got my O as 130. Like my opposite side is 130. So wouldn't that be my Y?
Except that we should have the same thing in the x direction. So that suggests to me that you drew yours wrong. It's possible you drew yours with the 30 degrees over here. But based on this labeling, the opposite side would have to be in the y direction, and the adjacent side would have to be in the x direction. Go ahead. I'm sorry, I couldn't hear the end of your question. No, if the wind's blowing hard enough, technically it can blow the plane in any direction it wants. Or if the plane's engines are powerful enough, it could push itself against any wind. But I want to get away from us thinking that this is just about, airplanes. I'm using them because they're easy. But you can add together any vectors of the same type. In fact, I would hope that will be in your notes. That it doesn't matter what it is we're adding together. When it comes to adding vectors, the process is the same. But we can only add together vectors of the same type. So in this case, these are all, velocity vectors. You can add velocity vectors together. Next week, we're going to be adding force vectors together. Our goal here is to be able to recognize that vectors have direction, and we can deal with that in 1 or 2 dimensions. Tanner, did you figure out your problem?
No.
Then I don't know what you're doing, because
I mean, I do it the same way, but the way that it's facing, the 30 degrees faces the opposite side, that's the y-axis, isn't it? I mean, that would be up for y.
yeah,
But you use the 130 for x.
the opposite side is on the y-axis. You're right. And sine is opposite over hypotenuse. And the sine of 30 is a half. And a half of 150 is 75. I'm looking right here.
Oh, I see what I'm doing.
Okay, I'm glad you can, because I thought it was in the twilight zone. All right, so I need a final little coordinate system. And these coordinate systems I'm drawing are just to help me deal with the math and all the data that I've been given. But, so I'm going to go out 168 in the x and down 43 in the y. My result is an arrow drawn from the origin to the tip of the last vector. Now, just be careful. I've been doing this for a long time. And there are a lot of people who, when they get their 2 vectors, instead of doing this, they would draw it like this. And that's going to mess you up, because what do you do now? I mean, yeah, you can make a triangle like that, but it doesn't make any sense. So you draw vectors when you're adding them together, tip to tail. So that's what I'm expecting right there. And then my resultant right there. So I want to get the result and the angle. Generally, again, you're going to need a calculator. Based on putting the angle there, this becomes the opposite side and this becomes the adjacent side. And this is my hypotenuse. So you can get Pythagorean theorem in here, but you're very likely to use the tangent if you want to get the angle, and I do. So I'm going to do 43 divided by 168, and I will do the inverse tangent to tell me that it's 14 degrees. And I'll just use Pythagoras because it's fast. So 168 squared plus, 143 squared. And then I take the square root. And I find that it's 173. I'm not done, but at least I have the resultant, 173, and the angle, 14. If I want full credit, I need to give reference. And that 14 degrees has me start facing east and turning towards the south. So I am 14 degrees south of east. You could also say just negative 14 degrees relative to the x-axis. You could say 76 degrees east of south. All of those are fine. To figure out which direction they go, Anybody in the classroom have a question? Go ahead, Tanner.
Yeah, why is it 30 you're at? You're 130, I mean, you're at